So today I'm going to talk about generalized or Q-Eulerian polynomials. And a digraph version, directed graph version of the chromatic quasisymmetric functions. Okay, so the first part of it is on the generalized Q-Eulerian polynomials. So for each R, going from 1 to n, we define inv less than R to be the number of inversions where sigma I is bigger than sigma j, but it's bigger by R, by less than R, I should say. So it's not too much bigger. So we're counting inversions that aren't too big in the letters. And then we're taking the descent set, where the descents have to be bigger than R. So this is the set of all I such that sigma I minus sigma I plus 1. Sigma I has to be bigger than sigma I plus 1. And but by at least R. That's the descent set. So the inversions are small and the descents are big. When R, oh, and I forgot one more thing, the major index, MAJ, bigger than or equal to R, is just the sum of the elements of the descent set. So when R is 1, inv less than R, there aren't going to be any, that's 0, because R, okay. And the major index, we're not restricting it at all. So that's the usual major index. When R is n, inv less than R, we're not restricting inversions at all. So that's the usual inversion index. And now we are restricting the major index. There's going to be no descents here. So this is zero. Now these statistics came up in the work of Don Rawlings in the late 1970s. So Rawlings statistics what he did is he added these two statistics together. So for all R, in N, he took the inv less than R and added to the MAJ greater than R. And he called this the R, I don't know if he called it, but we call it the R major index. This sum. And it interpolates between, as you can see from here, as you can see from here, it interpolates between inv and match. And what's cool about this R major index is just like inv and match on Mahonian permutation statistics, the R major index is also Mahonian. So that's what Rawlings shows. That inv is Mahonian. So they're all, for all R, these are distributed just like the inversion statistics. So in other words, Q to the inv plus match sigma in the symmetric group is equal to the Q analog of n factorial for all R. And he proved this with a generalization of Fuwada's classical bijection, taking match to inv. Okay, so it's so what we're going to do now is break this up into T to the inv times Q to the match. Okay. So when T, and we'll call this ANR QT. So when T equals Q, we get the Q analog of n factorial.
Michelle?
Yes.
If you take the Rawlings statistics, which is a sum, and fix a permutation and change R from 1 to n, then this list, does it have any monotonicity or not monotonicity, but bimodality, unimodality or something?
When R changes,
yeah,
you say.
For
Yeah,
a fixed sigma.
I don't know. I never thought about that. That would be interesting.
Thank you.
So, so if we look at AN2 QT, that's T to the inv less than 2. I'm going to write 1 here instead of. And if you think about what inv less than 2 sigma, we're saying we're counting inversions where the letters differ by 1. If we take the inverse of that permutation, then we're counting descents. So this is exactly equal to the Eulerian polynomial. We're counting descents. Okay, so the question is, what if I put the Q back here? what do we get? So this is a theorem of Sharesian in our paper. A to QT is equal to AN QT. And by that, AN QT was what I talked about in the first lecture. Those were the Q-Eulerian polynomials involving major index and exceedance index. So we get Q to the match. I'm going to do it with the inverse so that I can write descent instead of this, descent. And that's equal to Q to the match, the usual match, minus exceedance. Sorry, I'm squeezing this in. T to the exceedant, that's exceedance. That doesn't look like an A. T to the exceedance. Let me move this over. T to the exceedance. Sorry. Okay, so I think this was Teddy's question, whether there, and during the first lecture, whether exceedance, whether des had a partner. Let me write this neater. Let me rewrite this because it's kind of hard to read. This equals T to the exceedance. So whether des had a partner within this distribution, and the answer that I said I would answer during the last lecture is yes, this is the partner to des in the Q-Eulerian distribution given here. Okay. We could say I match is the partner to des. Okay. So how do we prove this? So let's recall in lecture 1, we showed that Qn, those Eulerian quasisymmetric functions, were the same as omega applied to the chromatic quasisymmetric function of the path. We also showed that the principal specialization, stable principal specialization of Qn using my modified definition is ANQT, is the Maj X Q-Eulerian polynomial, is this thing. And we did that by showing that Qn, by expanding this in the fundamentals, using a set statistic that I didn't define. But I said that this DEX statistic, if you sum DEX, DEX is a subset of the numbers from 1 to n minus 1. If you sum up the entries of DEX, you end up with Maj minus X. So that's all I said about depths. So this follows from that. Okay. So now we're going to use, so let me put this together. Hence, the principal, stable principal specialization of okay. Okay, so now we use something, 1 second. No, I don't want the 2. Sorry about that. Okay. Okay, so this is, so I didn't want the 2. Okay, so we have that that is true. And now we use omega xg xt from last time. Where G is the incomparability graph of a poset P. We had that last time. And in G of a permutation is, we had the definition before, is the, except I wrote it wrong, so now I'll write it correctly. It is the set of pairs, sigma I, sigma j, that are edges of G, set of edges of G such that I is less than j and sigma I is bigger than sigma j. The mistake I made last time is I wrote ij here instead of sigma ij. It's the letters that form the edge. But when I talked about this, I always treated it like the letters. And Bruce Sagan asked a question about that when I was doing an example, because I wrote it, I guess he observed that it wasn't consistent what I was doing with the definition. This is the definition I was using, and this is the right definition. Okay. And DESP, I stated this correctly last time, is the set of all I such that sigma I is bigger in the post set than sigma I plus 1. Okay. So using this, we can now take the stable principal specialization and get that this is T to inv G sigma Q to the sum of the descent, P of sigma. And for G equal to the path, G is that path, inv G is the same as inv less than 2 of sigma, because we're counting inversions where that are edges. We're counting the edges that are inversions. And so if it's an edge, that means it's close. The letters are close. Okay, and then P, G is the incomparability graph of a post set. That post set is the post set on N with I less than J in P if J minus I is greater than or equal to 2. That's the post set whose incomparability graph is the path. So des P of sigma is the same as des greater than or equal to 2 of sigma. And the sum that we have over here, the sum of that is equal to the major index. Thus, PS, they're taking stable principal specialization. Here, we have PS of omega X, the N path, sigma, XT is equal to A2 QT. Okay, so we have this. Oops. We had this. And over here, we had this. This. And this. So that shows that they're equal. That should be an N. So that's the proof. That's how we proved it. So I guess there's a natural question. I'm not hearing anyone ask, but the natural question is there a bijective proof? So what about for Wada's classical, his other classical bijection, taking des to X? because here we have joint distribution of deaths, and that statistic I talked about before. Here we have X and a statistic for the Q. So for what is bijection taking deaths to X, does that work? No, it doesn't. It's not that simple. It doesn't take the other statistic to match minus X. But fairly recently, Bajeni found a bijection that does work. So that was nice. Okay. Now, because of this result, when we have an R here, we're going to refer to that as a generalized Q-Eulerian polynomial.
Michelle, is
Yeah.
Foatas bijection working if Q equal to 1?
Yes, because it takes deaths to X.
Yeah.
So when Q is 1, it works. That's why we looked at that.
Yeah.
Okay. So, so we will oops. A and R, Q, T, generalized Q-Eulerian polynomial. So for each R, we get one of these Q-Eulerian polynomials. So let's recall from lecture 1 again that A and QT, which is the same as A with a 2 there, is palindromic, just like the Eulerian polynomials, and Q unimodal. So the difference of coefficients as a polynomial in T is going to be a polynomial in Q, and we're saying that the coefficients of that difference polynomial is positive, making it Q unimodal. So what about A, R, QT? Is that palindromic and Q unimodal? Well, palindromicity, that's pretty easy. As usual, palindromicity is often easy. Unimodality, Q unimodality, is not so easy. Even in the case Q equals 1. And I'll say why. It turns out it's true, but not so easy to prove, even when Q is 1. So
Michelle, what about a specific case like 2, now you take 3? Is that still hard?
Yes, I believe so. Okay. Even for 3. For R equal to N, that's easy, and N minus 1. So those specific cases are easy, but R equal small values of R, not so easy. So, let's let PNR equal P R plus 1. So remember these Hessenberg vectors that John talked about. I haven't really talked about them. So that's the natural unit interval order associated with this vector. When John and I wrote our paper, we did not call these Hessenberg vectors because we didn't know anything about Hessenberg varieties when we first started out. So we described these vectors. They were Hessenberg vectors. But when first started out, we didn't. And actually, that's where I'm leading up to, how we associated the chromatic quasisymmetric function with Hessenberg varieties, why we did that. And then GNR, we're going to let GNR be G. Okay, and so GNR is the incomparability graph of PNR. Okay. And so I is less than PNR, J, if and only if J minus I is bigger than or equal to R. So that's the poset relation, the order relation. And IJ belongs to the edge set of GNR if J minus I is less than R. Okay. So GN2 is the N path. Oh, sorry about that. Is the N path. Because the only edges are adjacent numbers when R is 2. And GN3 looks like this. Let me. We put these edges in. And that's what GN3 looks like. So the principal specialization of omega X G and R is equal to 1 over A and R QT. So that's where these generalized Q-Eulerian polynomials, how they relate to the chromatic quasisymmetric function. They're stable principal specializations of this special class of graphs. We could do this in the full generality of natural unit interval graphs, but I'm just sticking with this because I just find it simple to think about these polynomials rather than doing it for more general graphs.
Michelle, I have
yes,
just a general question. In your formulas for example, the last one, you're dividing by this n factorial, but q factorial.
Right.
And why are these formulas biased toward q? Why don't we have a t factorial?
because when we specialize, we replace the xi's by q to the I minus 1. So, and actually I modified this definition from the normal definition because in lecture 1, I wanted to just make things look simple in specializing. But really, this is supposed to be 1 over 1 minus q dot, 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 1 minus q to the n. But I modified it so it came out like this.
Okay, thank you.
Because this specialization is relying on q. So okay, so that's where these polynomials come from. They come from specializing omega of the chromatic quasisymmetric function. So in order to show that this is q unimodal, what we need to know is that this is Schur unimodal. And that was implied by E unimodality of the chromatic quasisymmetric functions. So because this implies that ANR QT is Q unimodal. When you specialize a Schur positive symmetric function, you end up with Q positive coefficients. So since we're taking differences and we have Schur unimodality tells us the differences are Schur positive, that's going to tell us the differences of coefficients are Q positive, and that's what we need here. Okay, so as in John's lectures, he showed that we can prove Schur positivity by using P tableau. But we didn't prove Schur unimodality. We didn't have Schur unimodality. We only had Schur positivity. So our hope at the time was that Schur unimodality could be obtained by generalizing the relationship between x of the path and the toric variety. I talked about this, I think, in lecture 2, the toric variety associated with the permutahedron. The result, we used the result of Procesi and Stanley to get this relationship, because this was just, okay. And then using the unimodality would follow from the Hard-Lefschetz theorem. So it's the representation of the symmetric group on the cohomology of that toric variety. And then the Hard-Lefschetz map respects the action of the symmetric group. And so we get from that we get Schur unimodality. So John and I wanted to find a variety that generalizes this relationship. And we didn't know about Hessenberg varieties, but we came across Stanley EC1 exercises, EC1, exercise 1 point in chapter 1, 1.50 F, and that's a 4-. And the problem was to prove that this polynomial is unimodal. So that was exactly our ANR1T. And we didn't know that that polynomial had ever been looked at before. And we saw in Stanley, according to Stanley, it's unimodal. So didn't know how to prove it, that exercise. It was a 4-. It was quicker to look at the solutions than try to figure, we didn't know how to prove it, we knew that. So looking at the solution, here's the solution that appeared in Stanley. It's the Poincaré polynomial of the regular semi-simple Hessenberg variety. Consequently, by the Hard-Lefschetz theorem, it's unimodal. Well, that was the first time we heard about Hessenberg varieties. But now we were looking for just such a variety. There's Hessenberg varieties generalized. They were introduced by Damari and Shaman in this special case that we're talking about now. And the Damari and Shaman called these generalized Eulerian polynomials. So now we had a great clue. That's what we want to look at, Hessenberg varieties. And by the way, Stanley asked, is there a more elementary proof of unimodality? And as far as I know, no one's has come up with a more elementary proof. This is the only proof I know of that this is unimodal. If anyone's seen another proof, I'd be interested in knowing. Okay. So we now knew to look at Hessenberg varieties. And we knew that in order to obtain the Q analog, the Q, to be able to put a Q here and say it's Q unimodal, we needed to look at we need to generalize the relationship with the toric variety. And there we had a group, the symmetric group acting on the toric variety, on the toric variety. So we wanted a representation of the symmetric group on the Hessenberg variety, and we couldn't find one. And then we learned about Tomachko's work. she had a representation of SN on the cohomology, not on the toric variety, but on the cohomology. John talked about this. And so John explained exactly what this was using GKM theory. But once we found out about Tomachko's representation, that turned into our conjecture. So this is how our conjecture relating, I'm just giving sort of, again, a prequel, how our conjecture relating Tomachko's representation to the chromatic quasisymmetric functions was born. That's where it came from. It came from, because we were looking at the Q unimodality of those generalized Q Eulerian polynomials, we were led to this conjecture. Okay, so that's where the specialization brought us. I hope I didn't rush too much through that. In the time I have left, I want to talk about the chromatic, unless there are questions about this, because I'm sort of switching now. So I want to talk about the chromatic quasisymmetric functions for digraphs. Okay, so where this came from is considering the graph, which is the cycle graph, Cn. So now instead of a path, we have a cycle. Okay, the path motivated a lot of what we did. Now the cycle motivates the next phase. So Stanley, in his original paper on chromatic symmetric functions, proved the following formula generating function for the cycle. The chromatic symmetric function of that graph, the cycle graph, this generating function, he proved the following, is equal to this was back in 1995. He proved this. Consequently, from that formula, you can derive that the chromatic symmetric function is E positive. So here was an example of an E positive symmetric function that was not the incomparability graph of a poset. Okay. So my student and I were considering what happens. Do we have a refinement of this result? Can we get a refinement of this result? And this is the result that we got. Okay, so this is a T analog of this result. So what is, let me copy this, it's hard to, oops. Two T plus, I'm not even going to have enough room, let me write it down here. So these are T analogs of those numbers. Over okay, so let's compare it. The denominator's not too bad. It's clearly, the denominator's clearly a T analog of the denominator here. But the numerator's pretty yucky. It's not hard to see that you end up with this when you set T equal to 1, but it's not pretty at all. But the consequence of this that the chromatic quasisymmetric function of the cycle is E positive. And so here was an example of an E positive chromatic quasisymmetric function that doesn't come from an incomparability graph. So this started off as a conjecture of Brittany Elsie, and she spoke on this at the combinatoric seminar at the University of Miami, and Richard Stanley was there. And of course, this isn't very pretty, the numerator. And he felt that it would be more natural to view the cycle as a directed graph instead of a labeled graph. Right now, the ascents depend on the labeling of the graph. But it's really, the only thing that really matters is an orientation on the edges of the graph. So let me say this more specifically. So every labeled graph, the kind of graphs we've been looking at, can be viewed. So this was Stanley's suggestion. As an acyclic directed graph by orienting edges ij, an edge, just had an undirected ij as I j if I is less than j. So just orient the edge, just put a direction on every edge if I is less than j. And now the ascent set of a coloring, when we color, remember if the coloring was consistent with this, then we called it then we said there was an ascent at that edge. Well, now the coloring has to be consistent with this. So this is, now we're looking at all the edges, ij, of this directed graph, of this oriented graph. We've oriented G now, for which the color of I is less than the color of J. So when I is less than J, we oriented the edge by putting it this way. And then we're calling this an ascent. So now the labeled cycle becomes, under this way of oriented, Let me draw it like this. Here's the labeled cycle. So we orient from smaller to larger, each edge. And then the edge from this edge here, if we're orienting from smaller to larger, we orient this way. Well, that's kind of unpleasant. We're going around this way, starting here. We're going around this way, and then we change direction. It's not so natural. So what happens if instead of doing that, we change that to that direction? We orient from N. So the cycle then gets oriented in the natural way a cycle should be oriented. And let's call this directed cycle CN with an arrow. And when we do it this way, the theorem becomes the T analog of Richard's theorem now becomes with this definition of ascent and directing the cycle that way, we get and this is due to Elsie in her thesis. So that's a much prettier result than the one where we had the edge oriented this way. Orienting it this way, changing the orientation of that one edge, turned the theorem, the T analog of Stanley's result, into a very nice T analog. And so consequently, from that formula, XCN is E unimodal, is E positive, and E unimodal. Brittany and I used this result to, when Brittany proved this result, the not pretty one, was just a conjecture, but we ended up using this result to prove the other result. And the other is this, well, I don't really have time to say more about that. So, so now the natural question is, when is symmetric? Well, in her thesis, she shows that when G is a certain cyclic version of the unit interval graph of the natural unit. Well, graph xg xt is symmetric. So we take a cyclic version. So the natural unit interval graph can be obtained from these unit intervals. You form a graph when they intersect, and you label these intervals from left to right. If you do a similar thing on the circle, you take these arcs instead of intervals, and when they intersect, you label them, let's say, clockwise, and when they intersect, you have an edge of the graph. So you can get, so here's the nth one, and it's overlapping with 1. You can get, so this is called a circular indifference. The graph that you get is called a circular indifference digraph. And this was called a natural unit interval graph. So here's some examples. If we don't have a, well, all natural unit interval graphs correspond to a cyclic circular indifference digraphs. So this is more general than natural unit interval graphs. So if we orient the natural unit interval graph from smaller vertex to larger vertex, orient the edges that way, we get an acyclic circular indifference digraph. And here, let me just write another example. If we go around in the circle, so these are the edges, 1, 2, here are the vertices, and here's n. So we have this cycle. And then we connect 1 to 3, 2 to 4, say. This is just one example. 3 to 5 this way. This is a circular indifference digraph. So the conjecture now, that is if G is a circular indifference digraph, then xg xt is E positive and E unimodal. Okay, so this is more general than any of the other refinement of the Stanley-Stembridge conjecture. And Brittany proved that with this circular indifference digraphs are P positive, that omega and that this is P positive. So in the power sum symmetric functions, and she gave the coefficients with a completely different description from the way we gave and Athanasiadis gave the coefficients. She has no, there can't be P descents because there's no P. There's no posets. And there can't be left to right P maxima because there's no poset. So the coefficients described differently. They're the same, of course, they have to be the same when you restrict to natural unit interval graphs, but the description's completely different. And let me just finish with some open questions. Sorry, I'm running over, but it's my last lecture, so for digraph. One is P unimodality. Of course, E unimodality is open, but P unimodality. But we don't even have that for the original labeled graph version. But one thing we do have for the labeled graph version that John and I showed was sure positivity. We don't have it for the directed graph problem. And of course, and unimodality. We don't have this. Oops, C's missing. So the sure unimodality for the natural unit interval graphs came from the correspondence with Hessenberg varieties and the Hart-Lefschetz theorem. We don't have that for this more general setting, and we don't have a geometric interpretation. So this is now taking us, showing that geometry is not giving us the answers, but maybe there is some geometric interpretation. So we have this more general conjecture, and here we don't have a geometric interpretation. I should stop now. I'm very sorry I went over, but
no problem. Let's thank Michelle for all her great talks.
Thank you.
So any questions for Michelle before?
Yeah, I do. Can I ask, Jim?
Sure.
Can you go back to your, I have 3 questions. One is 2 are simpler. In the last term.
Which on the directed graphs?
Yeah, the one before this, yeah, before the examples. Yeah, this one. Are there other candidates where you have symmetry beside the cyclic version graphs?
So there's only the one that Brittany and I did, that cycle where the direction of the edge from n to 1 is not the natural direction on a cycle. Mm-hmm. Because the labeled graph forces us to have the edge be oriented from 1 to n. That's not going to be the cyclic version of a natural unit interval graph. So that's like the exception. It doesn't fit into any general theorem, that example, but I don't know of any other examples that don't fit into this.
I see. And the other is to go back to the generating function of your generalization of the generating functions. Yeah, the bottom one. This is the first question I have. This is just want to make sure I follow the numbers. If you have 2 t factorial t and kt, and then it looks like they cancel out and you only get k squared. So am I missing something?
Maybe I copied it wrong because it's not something I memorized. You're saying when t.
Yeah, put t equal to 1, then the 2 k's cancel.
T is 1.
Am I right or no?
I don't know. When t is 1 here, we have 2k, yeah. And here we have,
K squared minus 2k.
K, that's a T squared. So that
Yeah, that's
K
one.
times K minus 2, and here we have K minus, oh yeah, so then we'll have K squared.
Yeah.
I don't know, that shouldn't, yeah, and here, so something's off, you're saying.
Yeah. So
Yeah, I might have copied it wrong, but you can look it up in our paper. This is a
I see.
paper on Smirnoff word enumerators that we, Smirnoff word enumerators. I'll fix it before this gets posted. I'll check and see that if I copied it wrong. But all I can say is it might be a little different from this, but it's equally not pretty. It's equally ugly. So whatever.
And
what we
maybe
did.
since you're also posting, let's look at the next modification of this theorem. The next one. Yeah,
A pretty
here.
version.
Yeah. In here you have k minus 1 t, but there is no t on k. Am I missing something?
No, that's correct. The
That's
K
correct.
doesn't have it. Yeah. So it becomes K times K minus 1, the way Stanley had it.
Okay. Okay. Thank you. Thank you.
Okay, thank you. I'll make sure to fix that in the posted version.
Okay, great. So any other
thank you,
questions?
everyone.
Yeah, okay.
Well,
By the way,
there
I
are the
just got a-
questions. I'm happy to answer any other questions.
We were planning on having John talk on Tuesday. He just sent me a note that he can't talk on Tuesday because he's traveling.
Oh.
So, so
Oh,
not
I
sure.
didn't. Yeah, I
will
could. I
happen.
wouldn't have had to rush at the end. I didn't realize that. I had to finish today, and I'm sorry I went over. I could have finished up next time.
Okay.
So, yeah.
Okay. So I'm not sure what's happening Tuesday, but we'll be in touch about that.
Okay, and thank you everyone for your patience, and thank you, Jim and Anna, for the invitation to speak. It's been a privilege. Thank you very much. And thank you, John, for being my collaborator on all of this.
Yeah, so John left already because he had to meet an REU student. He also told me that. But anyway, on behalf of John,
I see. I thought
No.
he's
Oh,
here.
you are here.
Yeah.
Okay.
Yeah, I'm here.
Okay. But you can't talk Tuesday, right?
I cannot talk on Tuesday.
Okay. All right.
I'm very sorry. I just did not keep track of my schedule. I'm headed. So
how about Thursday?
I believe I will be able to do this. It is somewhat dependent on what kind of connection I have. I'll find this out and let you know in the next, by the end of today.
Oh, okay, great. Sounds good. Okay, everyone, have a great weekend. We'll be in touch about what's happening Tuesday. And in any case, sounds like Thursday, John will be speaking.
Okay, thank you. Bye.
Yeah.